I guess we can get started. A few of students here today. Okay, anyway, so today we are going to talk about the air dispersion modeling, but we are not going to focus on the math, but I'm going to focus on the concept. So first, I'm going to talk about the movement of the particles in the atmosphere, and then which include advection and diffusion. And then we are going to use these two concepts to derive a Gaussian free model. So this model is usually used to describe the movement of the particle in the atmosphere. But here I would like to introduce two methods. The first one is mathematical approach. The second one is a statistical approach. And then I will talk more about Gaussian free model. And then Gaussian free model is relatively simple, so we have some more advanced models. So I want to introduce a more advanced model, which is based on this Gaussian free model. And finally, if we have time, and we can have some discussions about the limitation or some future work for this air mode. And so first, let's look at advection. Based on the definition, advection refers to the transport of the substance or quantity by the bulk motion of a fluid. So in general, if we have a particle here, and we can see as the time goes from T0 to T1 or to T3, and this is a wind field. So basically we have some flows coming from left side to the right side. And in this case, we can see that this particle will just go with this wind field. So this process is advection, and advection can be described by this equation. So in this equation, JA refers to the flux of advection, and C refers to the concentration. U here refers to the wind speed. And from this equation, we can see that given the same concentration, if we have a greater wind speed, which means we will have a greater number of particles that's coming or going out. So this is intuitively makes sense. The next movement type is diffusion. So diffusion is the next movement of anything, and it could be the atom or the particle or maybe the energy from a region of higher concentration to a region of lower concentration. And I think intuitively, when we are speaking of diffusion, we may imagine something like this. We have a beaker with water, and then we add some dyes to this solution. Even though we do not mixing or disturb the water, we can imagine that the dyes will just diffuse and it will fill out the whole beaker, and finally it will be uniform, something like this. So this process is called diffusion, and we know that it is caused by the movement of the molecule. And diffusion is driven by the concentration gradient, and it can be described in this equation. So JD here refers to the flux of diffusion, and we have the K and the gradient of C. So again, C refers to the concentration, and K here, this is a diffusion coefficient. And we can see that the K here is a function of different directions. So in this case, we can see that no matter for which direction, the diffusion coefficient could be the same. But for some situations, the diffusion coefficient could be different. So if we put all this term together, it represents the flux of diffusion according to Fick's law. And so in general, diffusion refers to the expand of a very small point. If we have a point of so many particles, then it will expand with time. So it will be larger and larger. So far, do you guys have any questions? Yes.
What unit is flux?
So for the flux, let's just use this as an example. We know that the concentration would be gram per cubic meter. So, and the unit is like meters per second. So if we combine this unit together, that will be gram. So this is meter square and this is per second. So it means in a unit area of a unit time, how many particles or matters gets through it. Yeah, so this is the unit. So any more questions? No. And then by knowing these two effects, so for the particle, they have both effects. So basically, suppose we have a particle A or a group of the particle, they are very small, and then as the time going, we can see that at first, because it is in a wind field or the fluid field, it will move with the wind. So this is advection, and in the meanwhile, it will also expand or diffuse. So the movement will be something like this. And for this process, we can describe this mathematically. So we can start from the mass conservation equation. This refers to the concentration change with time. And this refers to the net flux. And this refers to the source strength. So like in this case, because we do not have a source always emitting the pollutant. So like specifically in this case, the source strength equals to 0. And we can see that the concentration change with time equals to the flux, and this is making sense. So in this equation, for the flux and J, it equals to the flux coming from advection and caused by diffusion. So J refers to JA plus JB. And we have already know that JA equals to C times U and JD equals to this equation. So we can just plug into this J and put this J back to this mass conservation equation. And finally, we can have this equation. And this equation is called advection diffusion equation because it includes the advection term and it also includes the diffusion term. And so this is a little bit abstract, so we can look at an example. So suppose we have the stack here and it will emit the air pollutants. And from this picture, we can also see that the wind is blowing in this direction. So in this case, the advection refers to the particles that move with this wind. And we can also see that the size of the plume, like in general or on average, the size is increasing. So this is reflected by diffusion term. And here is the source, because for this one, we always have some particles of air pollutants coming out from the stack. And this is a concentration change with time. And so this is a advection diffusion equation. Do you guys have any questions so far? Now we have this question and we want to solve this question, to solve this equation. But we know that this is a partial differential equation, which is not quite easy to be solved. So to solve this equation, we need some simplification. So to simplify it, we add some assumptions to it. Let's just look at this one by one. So for the first one, we assume there is a constant emission rate. In other words, when the stack is blowing out some of the air pollutants, we assume the amount per unit of time it is constant. It will not change with time. So basically, the Q, we can just consider it as a constant. And then for the wind speed, we assume the wind velocity is also uniform. We use wind velocity, not wind speed, because the wind direction is also not changed. So basically, we have the very uniform wind field here, even the magnitude or the direction will not change. And the third one is diffusion. Diffusion is negligible compared with advection. So in this case, we know that even though some of the particles will go in with the wind, and because of diffusion, we have some particles go to this direction, and we assume that the speed of this diffusion is much smaller than the speed of the wind. So if this is Vd and this is Va, we can see that Va is much larger than Vd. And the fourth one is that the wind velocity and other meteorological parameters are independent of time. So in this case, because we know that like different weather condition or the different some like temperature gradients, they will influence the diffusion of the air pollutants, as we mentioned in the last lecture. So we just assume all of the meteorological conditions, they are the same. So they do not change with time. And the last one is the contaminant is reflected from the ground. Suppose like we have the ground here, we know that if the air pollutant hits the ground, it may be absorbed by the surface of the ground or by the grass or something. But here we just want to simplify it. So we assume when the particles hit the ground, it will reflect it completely. And here are the assumptions. And to solve this, we also need some boundary conditions. So like first one, we assume that the concentration approaches to zero when we move infinitely far away from the source. So in other words, if I'm very far away from this pollutant source, I assume the air is clean in my sight. So we can see that for the geometrical scale, when it approaches to infinity, the concentration should always be zero. On the other hand, we also assume no contaminations as x smaller than zero. So let's just say this is like for the wind direction, this is x direction. And if I am at the upwind direction, so we can say that at this place, the air is very clean. So no air pollutants will going against the wind. And the last one is contaminants cannot penetrate the ground surface because they have already assumed the flow reflection. So there is no particle that is going down from the ground. And this is a flux. So the flux should be equal to zero. So basically we have all of these additional assumptions and additional boundary conditions to solve this equation. And the method, like the exact method to solve this equation, I'm not going to talk about. So I'm just going to show the result. And the solving process is presented in this paper, and I have uploaded on Canvas. And the analytical solution is something like this. So we can see the concentration is a function of x, y, z, which is the coordinates or the position of a specific point. And so this equation is a little bit tricky and complicated, but if we look at this, we can find something. Let's say if we have a normal distribution. So for a normal distribution, the probability density function, like fx, we can say that it equals to like 2 pi, I think it has a square root or something. And then we have x minus mu. Mu here refers to the mean, and then the sigma square. And this is exp of something like this. So we can see that this form is pretty similar to this expression. Like we have something like 2 pi here, and we have x minus mu. So we have like the variable minus h. H refers to the height of the stack. And then we have some sigma square here. So because this form is pretty like the normal distribution, and we know that normal distribution is also called Gaussian distribution. That's why it is called the Gaussian plume model. And based on this form, we can see that we have 1, 2, 3. We have 3 Gaussian distributions. So intuitively, it is something like this. So this is the x direction, this is y direction, and this is z direction. We can see that along the y direction, we have this normal distribution, and along z axis, we also have another normal distribution. So these are the 2 normal distributions in this plume. And what's the third one? The third one is about the reflection, because they have already assumed that the plume, the particles will be fully reflected from the ground. So we have a mirror source here that is under the ground. So it will also generate some plumes here. So the third Gaussian plume, the third Gaussian equation reflects the reflection. So in this equation, we can see that Cx by Z is a pollutant concentration, which is a function of the position. And Q here refers to the source strength or the emission factor, which reflects how much of the air pollutant is coming from the stack. And based on our assumption, this Q is a constant. And here, H refers to the height of the source. So in other words, H refers to the here. And we also have something like the small h. The small h refers to the height of the stack, and the big H refers to the height of the plume. And intuitively, we can imagine that when the plume is emitted from the stack, it has some vertical speed. So as it's increasing, the vertical speed will gradually decreasing and become 0. So we have this height to represent the final height of the plume. And we also have this sigma x, sigma y, and sigma z, which is the standard deviation of the distribution concentration in y and z axis. And the sigma x and sigma y can be expressed in this equation. And this is a little bit tricky because they are derived from the Laplace transformation processes, and they are difficult to determine analytically. So in practice, for this standard deviation, we use empirical methods to determine it. So we have in this equation, Q is a constant, which is easy to obtain. 2 pi are the constants that we know, and U is the wind speed, which is easy to measure. And we have the Y and Z here, which are the coordinates. We already know it. And for the H, it can also be observed or obtained. So the only thing that we do not know are the sigmas. So for the sigmas, we usually determine it empirically. So here are some graphs of like the sigma y and sigma z over different distance. So we can see that as the distance increasing, the sigmas will also increasing. And we also have like A, B, C, D, E, F, different categories. So this different category represents different weather conditions. Like we can imagine that under the sunny day or under the cloudy day, the plume will be a little bit different. So these different letters represent different categories. And on the other hand, as I mentioned, as the distance increasing, the sigmas are also increasing. We know that if the sigma of the normal distribution increasing, so for this one, the sigma is larger than the sigma here. So the plume will be very fat, will be fatter. In other words, the pollutant concentrations are more uniformly distributed along the space. And this is also reflected in this graph. We can see that for the plume that is relatively closer to the source, we can see that this normal distribution is relatively narrow. But as the distance far away from the plume, the sigma become larger, and this normal distribution become fatter, which means the pollutants are more diffused or more scattered in the space. And so far, do you guys have any questions? No. So I think when we are talking about this approach, this is very that's fun. So sometimes we may feel something like this because it has a lot of math and this is not quite intuitive. So I'm going to talk about another approach, which is a statistical approach. And this is based on the random walk. So in this case, let's just suppose I also have a particle here as T0. And let's just say because of the turbulence in the air, we know that it may go up or it may go down, and it may go up and down at different speed. So maybe at T1 it comes to here, at T2 it comes here, T3 it's here. So it will be something like this. So, and if we have a lot of particle, that should also be something like this. And this process can be described mathematically by this equation. So we can see that as x0. So basically, let's just say this is an x-axis, and this is the 0. So we can see that the 0 here refers to the time step equals to 0. So at the very beginning, this point is at 0. And then we can also see that the new time. So this is a step before, this is a step after. So the next step equals to the previous step plus a eta term. And this eta follows a normal distribution. So basically this eta can be considered as a random vertical speed. And in this case, we can prove that the xt, so if we release different like particles from this position, and we can prove that the xt follows a normal distribution. If we catches all of the particles, maybe here, we can find the particle numbers follows a normal distribution here. And the mean will be equals to 0. And the standard deviation is something like is a function of t, because we can imagine for this one which has a short time, we can imagine the concentration may be something like this. But for a long time, the distribution will be like this. So I'm not going to show the proof of this equation, but I'm going to show a demonstration. So if we make this main field like as a vertical field, and if we have a particle here, so this process is pretty similar to what we have seen in like statistical class, and this is a golden board. So like we have many balls, the number will be something like this. So do you guys remember what's the distribution of the number of balls in this in here? Do you guys remember? No. So this distribution is binomial distribution. So, and we know that there are many distributions in the statistics. And if we find the binomial distribution, it will be something like here. And we also know that the binomial distribution could be approximated by a normal distribution, as long as the sample size approaches to infinity. So in our case, we have air pollutants or the molecules or the atoms. They are like even for a small amount, a small volume, they have a very large number of these particles. So basically, this is satisfied. So this process can be approximated by a normal distribution. And here is the simulation example. So suppose we have one point start from here, and then let's just let it have some random walk. And this is for the 100 step. and we can see the trace is something like this. And then let's just say we have 100 simulations, like we have 100 small particles. It will be something like this. And we can imagine that if we just take the samples from here, the distribution will be something like this. So they are very concentrated in the center. But if we take some samples at the end of this plume, we can imagine it will be something like this. The particles, they are more spread. And in reality, we will have something like this. So this is a picture of the instantaneous plume. And we can see because of the turbulence or some disturbance, the plume are like discreted and it is very irregular. But if we take many pictures and overlap them together, so this is a cumulative concentration of the plume. And we can see that this shape is pretty regular. And we can also imagine that the concentration are very concentrated here, and the concentration are relatively spread here. And again, this can be described by a normal distribution with the mean equals to, it just equals to the position of the source and the standard deviation sigma. And this sigma can be obtained empirically. So again, we can find this table to determine the sigma of this Gaussian plume. So again, we can still go back to this plot. Again, this is a normal distribution in the horizontal direction, and we have normal distribution in this vertical direction. And I personally think this approach is more intuitive and is to this model. So far, do you guys have any questions? Yes.
So for the random walk, did you consider that the molecules can hit each other?
No, we consider they are independent.
Okay.
Yes. And I think in reality, in the air, I think the particles are very rare to hit each other. Then, so basically, we have two different independent approaches, and finally, we can derive the same thing. So I think this is the interesting part of the air dispersion modeling. So let's just go back to the Gaussian plume model. So the expression of the Gaussian plume model is this, and we have already talked about. And then it is the assumptions. So here let's just recall the assumptions first. We assume the constant emission rate, and we assume the wind velocity is uniform, and we also assume there's a relatively large wind speed, so the diffusion is negligible in terms of the direction of the wind speed. And because of the meteorological conditions, they are independent of the time, so the plume is in a steady state. And finally, we assume the contaminant is reflected from the ground. And for this model, it has some advantages. Like it has relatively simple input, and it is computationally less intensive than some other dynamic model or fluid model. And I would say this is accurate. I put a star here because the accuracy requirement depends on what we need. So I put a star here. And we can see that if we are searching for application of Gaussian plume model, and we can see there are a lot of literatures. So this is widely applied in the environmental field. And on the right side, this is also another example from this paper. So this is a deposition or the concentration of zinc from different stacks. And we can see if we have multiple sources, we can just calculate them differently and then add them together. So, but we can see that for these assumptions, they are very strict. For example, it assumes the wind velocity is uniform, but in reality or in practice, I think this is impossible to have the very uniform wind velocity. We know that the wind direction may change time to time, and the wind speed will be different at different heights. So in engineering, we can make this less strict. So as long as this is pretty similar or pretty close to these assumptions, then we may use this model. So basically, we just loosen the assumptions. So we have the relatively constant emission rate. So if the change is relatively small, then it is good. And relatively uniform wind velocity and relatively large wind speeds and the meteorological parameters, they are also relatively constant in a specific period of time. And then we have the negligible precipitation and absorption from the ground. And here, we also have a hidden assumption that I didn't mention in these two processes. So I'm wondering, do you guys think what will be the assumption that I didn't mention? Do you guys have any ideas? Like during these two processes, during these two derivation processes? And I think Amir mentioned like the particles, they do not have some interaction. I think that should be one of the assumptions. So basically another assumption is that we assume the particles or the air pollutants, they are coming from a point. So they always start from a single point. In other words, we can also assume the size of the source is very small or is small compared to the spatial scale of the transportation of the pollutants. In other words, if we have some source that is very large and we are interested in the concentration at two different locations here, then because this distance is pretty similar to the scale of this source, then we may not be able to use the Gaussian model. And so the full name of this Gaussian model is called the point source Gaussian model. And so for here, do you guys have any questions? And so in summary, we start from the mass conservative models, and then we add some information of the particles like the advection and diffusion. Then we can derive the Gaussian model. And then if we add some more information to the Gaussian model, we may get the air mode. We may get a more advanced or more accurate models. So basically, these models can something like the evolution. And here I'm going to briefly talk about the air mode. So air mode the full name of air mode is American Meteorological Society Environmental Protection Agency regulatory model. So the name is relatively long, but the key point is that this is a regulatory model. So again, for the regulatory model, this is preferred for the government staffs because this is also equally defensible. And here's a full description because this is based on Gaussian model, so it's pretty similar. This is a steady state model that incorporates the air dispersion based on the planet boundary layer and blah, blah, blah. I'm not going to read this. But we can see that the general expression of air mode is something like this. And the XR refers to the position of the receptor. So basically, this can be expressed as like X, Y, and Z. And then we have this XP. So XP refers to the position of the receptor with the parent. So for the Gaussian model, we did not consider the like if we have some mountains or if we have some elevation change of the ground. For the Gaussian model, we do not consider this. But for the air modes, it considers this effect. And we can see that for the air mode, it is just the combination of two results of Gaussian pre-model. And for this one, this is a Gaussian pre-model results without the influence of the terror. And this is a Gaussian pre-model with influence of terror. And then we just assign like the weight factor to these two concentrations, and then we can get the final concentration. And for CC and CS, so for CS, it is the Gaussian pre-model under stable boundary conditions. And for the CC, it refers to the Gaussian pre-model in convective boundary layers. So like we have different types of the boundary layer. And this is for the stable boundary layer, it is relatively simple. So we only have one Gaussian pre-model for each one. But if it is under the convective boundary layer, then this Gaussian pre also have three small Gaussian films, and it represents CD, CI, and CP. So here shows the situation with three small Gaussian fields. So we have the direct source that will generate the Gaussian field, and we also have the penetrated source that will also generate the Gaussian field, because we have some particles will penetrate into the boundary layer of the atmosphere. And then we also assume like we have some reflections, but this reflection may have some delay. So we also have this indirect source. So basically in this situation, we have three different and small Gaussian plumes, which is summarized here. So we can see that this model is relatively more complicated, but it's considered more situation. So it is also widely used. And here I just want to show some of the effects of the terrain or the buildings. This picture shows the wind flow up under the building, and we can see that they are pretty irregular. But for the winds behind the building, we can see that we have some wind flows coming down to the building. In other words, if I'm standing on the lee side at the bottom of the building, we can still receive the wind. And this is a more detailed study. So this is adopted from a paper. We can see that if we have a building here and we have the wind flow here, we can see that because of the building, we will have some downwash or the side wash at the back of the building. And we can see that the wind flow is relatively strong here. So I think maybe we have some daily life experience, like if this is a very windy day and we are standing on the back of the building, and we may feel that the wind is relatively strong. And on the other hand, sometimes if we have some leaves or some dust on the ground, we may feel like there are lots of dust coming to us. I'm not sure if you guys have the same feelings, but in general, we may have this effect. So in other words, because of this downwash or sidewash effect, the concentration of the pollutant, they may accumulate it at this position at the lee side of the building. So in this case, the Gaussian pre-model did not consider that, but for the air modes, it considered the effect of this downwash effect. And so the air modes include influence of terrain and buildings. And because this process is relatively complicated, so the air modes just use some empirical methods to consider this. And so in summary, this is a regulatory model, and for the air modes, the source code can be found like from EPA, and it can also have some commercially available softwares. Because of the time, I'm not going to show the demo, but basically we can just input the data of the terror, input the data of the building, and it can be used to show some film animations, and the results can be expressed or displayed on Google Earth. And because the air mode is based on Gaussian pre-model, so the assumptions are pretty similar. I put a star here because it has some extra assumptions, but in general, the assumptions of air modes inherits from the assumption of Gaussian pre-model. And again, it is also relatively simple compared with some other dynamic models and computationally less intensive. And this is also considered as accurate. And again, if we are looking for applications of air modes, and we can also find some many research doing this. So this is also a widely applied model. So we have a little bit time, so let's just look at this question, look at this statement. So basically, for most of the cases, by knowing the assumption of the model, then we can determine if the model is applicable for the given situation. And I think this is not only for this model or for this course, I think this is also applicable for other stuffs. So if they want to say, can I use this model to solve this question? I think the first thing that we need to think is, what are the assumptions of this model? Do our data, do our situation satisfied with this situation? So if the model has some problems or have some unexpected results, we may analyze where is the source of the uncertainty, or how can we improve this model? And here, let's look at an example. So let's just show the continents of Asia and Europe. So let's just say, can air mode be used for modeling the transport of pollutants for a large spatial scale, like from Europe to Asia? For example, if I have a stop here, and this is in like Germany, something like here, and then we have some people here, like in the Russia, and then we have the pollutants coming to here. So in this case, our question is, can I apply air modes to predict the concentration from here to here? How do you guys think? And here is the assumption of the air mode I just listed here. This is the so basically, when we have this situation, let me just compare it one by one. So let's just say it assumes the constant emission rate, and we can say we actually we don't know if the emission is constant, but let's just assume it is constant. But for the next one, it assumes the wind velocity is uniform. So basically, it assumes the wind is uniform in this large area, and we know that the wind will not be uniform in a very large scale because of the Earth, like the rotation of the Earth. So basically, this assumption does not satisfy. So because this assumption does not satisfy, in general, we cannot apply air modes in this situation. And when we look at some other things like relatively large wind speeds, this may satisfy. And the steady state, it assumes the meteorological conditions, they are the same. But again, maybe it is in the daytime here, but it may be in the nighttime here. So the meteorological conditions, they are quite different. So this assumption does not hold. And the contaminant is reflected from the ground. For this one, we do not quite sure. So let's just say maybe, and the point source emission, because it's a large scale, so we may say that this may satisfy. But because we have some assumptions that is not satisfied in this situation, so we would say we cannot apply air modes to this situation. And we may also have some other situations, like if we are interested in the concentration from in a river or in a lake, in the water. And we may also have some situation. Oh, so we only have two situations. Okay. So I'm not going to go through this. And finally, I want to talk about some ending notes. So for quiz 8 and quiz 9, they are due today, I think. And for assignment 6 and assignment 7, they are due on next Monday and next Thursday. And again, for this assignment, we do not have homework assignment for the air pollutant units and quiz term, but they have a quiz. It is due on the Thursday, 2 weeks later. And for the next week, on next Tuesday, my current plan is to do some introductions of independent projects. And I also plan to distribute the air sampler. So for the independent projects, each group will have a air sampler. So on next Tuesday, each group should have at least 1 student come this class in person so that I can distribute the sampler. But I will also discuss with Maria to say how many samples do we have. So this may subject to change. But if there's any changes, I will send the announcement. And on next Thursday, I'm going to talk about like data presentation that may be useful when we are preparing for the final presentation of the independence project. And then the next Tuesday, we are going to have exam 2, and I'm working on that. So I will provide more information in the lectures and in the next week. So that's it for today.